Hi, this is John Gardner. I'm a professor of mechanical engineering at Boise State University, and welcome to another video in our series on industrial refrigeration systems, brought to you in part by the Industrial Assessment Centers of the Department of Energy. What I want to talk about today is about the condenser, which is the unit that rejects the heat from industrial systems. So as you'll recall in our discussion, most of these industrial cooling systems use some form of the vapor compression cycle, the refrigeration cycle, using a refrigerant that at low pressure boils and absorbs heat, and that's how the heat is removed from the space you want to cool. And then after it vaporizes, after it evaporates, it's then compressed to high pressure and very high temperature with a compressor, mechanical compressor, and then that vapor is then condensed in a place where it can reject the heat, which is the condenser, not surprisingly. And that condenser is outside, usually in a rooftop or on a concrete pad next to the building. I just threw this little cartoon here so you can, again, familiarize yourself and remind yourself of what the different components look like. In the cold space is, like a refrigerator, freezer, these things are behind the panels inside the freezer. But, walk-in freezer in an industrial setting, you'll see these usually hanging in the ceiling or on the back wall. So large fans blowing air through these coils, and this is where the refrigerant evaporates. That's where the refrigeration takes place. That vapor then, cold vapor then goes up into the compressor, where it is compressed, not surprisingly. It's hot and at a high pressure. And this is a typical rooftop unit. This is like a side draft evaporative cooler. The air gets sucked in here by these fans. You can see, if you look closely enough, you can see they're belt-driven fans. These are kind of old-fashioned. More and more we're going to designs where there's axial fans on the top with direct drive motors. But this is still pretty common. You'll see these all the time. The air gets sucked in here, blown out the top. Water's recirculated through this plumbing on the side. We'll talk more about that. There's a metering device of some kind that basically divides the high pressure system from the low pressure system. And when it expands through that device, it drops to low pressure, but also it gets very cold. And that's the basis of the refrigerant effect. So these rooftop units can be air-cooled or evaporative in nature, which is a combination of air and water cooling. The ones you see at home, sitting out on a little concrete pad next to a small office building or next to a house, those are strictly air-cooled units, but they are condensers. The capacity, the ability to dissipate heat can be greatly enhanced if you spray water in the vicinity, let it evaporate. And as that water evaporates, it takes heat away. It absorbs the latent heat, the heat of vaporization of water. So there are devices that bring those two together, and they are called, oddly enough, evaporative condensers. It sounds like an inherent paradox, but the idea is the water on the outside evaporates to help carry the heat away. The refrigerant inside the pipes condense. And again, here's a couple more pictures. This one I took from Johnson Controls. This is what I was referring to earlier with the fans, axial fans at the top of the unit, drawing air. They draw air. These are called induction style. The air gets drawn in this black area here. There's usually filter screens of some kind to keep trash from getting into them. Air gets blown out the top. The refrigerant goes through these areas here, and this plumbing in the side is the water recirculation system. Here's a cartoon of it. So we see a sump, the tray at the bottom of this unit here, and shown here in dark gray. A pump that pumps the water out, takes it to the top. There's a series of sprayers at the top that mist the water, so it's fine mist as it comes down and onto these coils. And in between the coils are usually, it's called fill, kind of corrugated plates of plastic or aluminum, and the water spreads out on the fill and falls down along the fill. The fill is usually oriented vertically. So the air comes up along the fill, the water comes down along the fill. So the air starts evaporating the water away, and meanwhile the coils are moving along throughout the fill and conducting the heat away from the refrigerant. So let's talk about what's happening in the condenser. How does that heat move? So heat flows from higher temperature to lower temperature. That means that the refrigerant inside the pipe, that hot gas coming from the compressor must be at a temperature that's higher than the ambient, right? Than the environment. And by the environment, I mean the immediate environment of the condenser. If all you're doing is blowing air through the condenser, then it's pretty much just the temperature of the environment. The air speed helps increase the convective coefficient, but the temperature is pretty much the same. The difference between the condenser fluid temperature, the refrigerant temperature, and the environmental temperature is called the approach. Okay, so if the refrigerant is 20 degrees higher than the ambient temperature, then you say the approach is 20 degrees. And in these big ammonia systems, they're usually 20 to 30 degrees. Pretty big approach. So in these smaller systems like chillers that they use in commercial buildings, home air conditioners, the approach is generally a bit smaller. In these, I did some research for both Baltimore Air Coil and for Evapco, and if you look at the specifications for these rooftop evaporative condensers, you'll see that they're specified at their ability to reject heat at an approach of 30 degrees Fahrenheit. In other words, if it's a 600-ton unit, it can dissipate heat at a rate of 600 tons of refrigeration capacity if the approach is 30 degrees. So let's talk about the temperature, because when you have these evaporative condensers, when the water is being sprayed on there and it's evaporating, it lowers the immediate environment, the temperature of the immediate environment inside the condenser. In other words, it could be 90 degrees outside, but if you have these evaporative coolers where the water is being sprayed down and evaporating, then that lower temperature, then the temperature that the condenser coils see that drives the heat transfer is actually lower. And in fact, at a limit, it's called the wet bulb temperature. So let's review what we mean by wet bulb temperature. So first of all, let's talk about the dry bulb temperature. That's the temperature that's commonly reported. You know, the newscaster, the weather forecaster says, you know, the temperature today was 72 degrees. That's the dry bulb temperature. It's, you know, thermometer with nothing, with, you know, a dry mercury bulb is what that refers to. Then there's two other temperatures that are associated with dry bulb and humidity, and that's the dew point temperature and the wet bulb temperature. They're related in that they're both related to the humidity content of the air, but they're not the same. And I want to take a few minutes to talk about that. So let's go back to our thermodynamics and imagine kind of two different thought experiments. One is a sealed control volume, totally insulated, no heat transfer. And inside the control volume is an air water vapor mixture, but there's also some liquid water at the bottom of it. And we have a mechanism, and I won't specify what that is, it's just a thought experiment, that drives some of that water, liquid water, into vapor into the air. So in other words, we're adding more and more vapor into the air. But we do that without adding any heat. So that there's no heat transfer going on in there. And as that liquid water changes to vapor, it absorbs the heat from the air, and the temperature drops. And that process continues until the relative humidity is 100%. In other words, until that control volume, that chunk of air in the control volume, can no longer hold any more water. And since some of that water evaporated and absorbed heat, the temperature is lower. And that temperature, when it gets to saturation, is called the wet bulb temperature. The second one, the dew point, is a different thought experiment. Again, imagine a control volume of air. In this case, it's not insulated, but it's a water vapor mixture, an air water vapor mixture, and we pull heat out of it by cooling. Okay, so we let the heat flow out of it. The temperature of that mixture drops to the point again where the relative humidity is 100%, and the water vapor spontaneously condenses out. That's called the dew point temperature. In our weather phenomenon, that's what happens when fog forms in the air. So if you remember the psychrometric chart from thermodynamics, it's a way of looking at mixtures of dry air and water vapor. So it's very busy, but the main temperature scale is along the bottom here, and it's in Fahrenheit. So these small numbers you can read sort of vertically. So here's 80, 85, 90. These vertical lines are the dry bulb temperature. Horizontal lines are humidity ratio. So it's a mass of humidity in the air relative to the mass of the air, mass of water relative to the mass of the air. These slanting lines here that are kind of 45-degree angles, those are lines of constant enthalpy. And these more steep lines are, those are volume ratios. Not as interesting. So the main thing we want to look at are lines of constant dry bulb temperature, lines of constant enthalpy, lines of constant humidity ratio. Okay. Any point on here is a state, a thermodynamic state. So all you have to do is specify two of these, all these various quantities, and it specifies a state. Oh, one more thing I want to show you, the lines of relative humidity. So these curving lines are lines of constant relative humidity. So here's 40%, 50%, and as you get to the extreme, this 100% is the mixture. It's the saturation. You can drive no more water vapor into the mixture. And there's a temperature scale that you read off of that, which is it's the same scale for wet bulb and dry bulb. And I'll show you how that works in a second. So let's best way to look at this is an example. So 90 degrees Fahrenheit, 40% relative humidity. So that's this spot right here on the screen. So you've got 90 degrees Fahrenheit dry bulb. This line here is the 40% relative humidity line, and where those two intersect specifies the state of the system. So to find the wet bulb, remember we want to find a point on this curve that corresponds to that thought experiment, that point of increasing the humidity ratio, but not changing, but not by adding heat. So it turns out that's a line of constant enthalpy. So that proceeds along this green line I show in here and intersects right about here. So it looks like, I don't know, eyeballing that. Here's 70 degrees on that. There's 75. So it looks like about 71 degrees Fahrenheit is the wet bulb temperature associated with that state, 80 degrees Fahrenheit, 40% relative humidity. Dew point, remember, is lowering the temperature, but not changing the humidity ratio. So the amount of water that's in that mixture remains the same. And we move along, So we move along this line of lower and lower dry bulb temperature and into the point of saturation. And that looks like it's around 62 degrees Fahrenheit. And indeed, that's pretty close to being right. So it's at 90 degrees Fahrenheit, relative humidity 40%. The wet bulb is 71 degrees. Dew point is 62. There's online calculators. Here's one I've found from the Dayton ASHRAE chapter. Lots of other ones out there. Go ahead and try that out for yourself and get a sense for that. But keep in mind that a couple things. Wet bulb temperature is going to be higher than the dew point. They're both lower than the dry bulb temperature. And as you get more and more relative humidity in your ambient environment, the three temperatures converge. Okay, so at 100% relative humidity, dry bulb, dew point, and wet bulb are all the same. Okay, so let's dive a little deeper. Let's look at what's going on in these condensers, and specifically the relationship between what's going on in the condenser and what's going on in the compressor, because that's the key to understanding energy efficiency in these systems. We know that heat transfer goes from higher to lower temps. That's obvious. The vapor leaving the compressor is very hot. It's superheated vapor, right? It's well into the superheated region. What determines the pressure at the output of what's called the discharge pressure, and it's the same as the condenser pressure? And the answer to that is that it's the pressure corresponding to the temperature, the saturation temperature, that allows the heat transfer in the condenser to reach an equilibrium. Let's talk about what that means. So if you're modeling a condenser as a heat exchanger, this is the simplest equation for it. We look at an overall effective heat transfer coefficient. I call that U. And the heat transfer rate, Q dot, is that overall heat transfer coefficient times the temperature difference between the ambient temperature and the temperature of the refrigerant inside. Inside that U is a surface area term. There's also a combination of convective and conductive terms. So the velocity of the air going across the coils is embedded in that U term. T infinity is the ambient temperature inside the condenser. So if the water's flowing and it's evaporating, it's approaching the dew point temperature. And of course T5 is set by the pressure of your system. If you want to increase that heat transfer, you can do it three ways. You can make the condensing pressure, in this case I'm calling it T5, condensing pressure higher, which then raises the condensing temperature at a given T infinity, environmental temperature. That delta T then gets bigger. You can drive ambient temperature lower, and that's what an evaporative condenser does. It takes 90-degree air and makes it 70-degree air by evaporating the water into it, according to our example we just looked at. Or you can make U larger, and you can do that by increasing the airflow through the fan. So any one of those three things improves and increases heat transfer in the condenser. Remember the thermodynamics. This is the amount of heat that needs to be rejected. That's the mass flow rate of the refrigerant times the difference in enthalpy from the entrance of the condenser, or the exit of the compressor, and the exit of the condenser, which is that saturated liquid that's coming out of the condenser at the end. So it's mass flow rate times the change in enthalpy. This is a little more difficult to figure out how condensing pressure affects that. And it turns out, at least in the studies I've looked at, there's not a strong relationship. In other words, it's pretty flat. And here's one way to look at it. As you increase the condensing pressure, things happen in different directions. For example, as the pressure increases, that saturation pressure increases, the saturation dome on the enthalpy diagrams gets narrower, which means that HFG, the difference between the vapor and the gas and liquid phase, enthalpies, is smaller to a point until you get to the critical point when it goes to zero. So that means that delta H here can be driven smaller. But remember, H4 prime is actually in a superheat region. And in fact, as the pressure goes up, so does the temperature at the superheat. So this gets a lot higher. So that's offsets. These two tend to offset each other. As that condensing pressure gets higher, the compressors aren't as efficient. Okay, they're not positive displacement devices. So at higher pressures, they can't eject as much vapor into the system. So their mass flow rate falls as that goes up because the volumetric efficiency is lower, which tends to make this heat transfer get smaller, right? But as the compressor works harder to get to these higher pressures, the amount of heat that needs to be rejected also goes up. So there's factors pushing this number up as the condensing pressure gets higher, and factors pushing it down as the condensing pressure gets higher. And you can see where I'm going with this. If you combine these two equations, you get an equation that looks kind of like this. That on the left-hand side is what's going on in the condenser, heat transfer, and here's the thermodynamics that's bringing the heat to the condenser in the first place. And what we need to do is, well, what happens is it finds an equilibrium position. So let's think this through as a thought experiment. Let's say it's running at equilibrium, and the outside temperature gets higher, right? So T infinity goes up. Well, what happens? Well, this delta T then gets smaller. If all else stays the same, then the amount of heat transfer goes down. That means this has to change too. Okay, if the amount of heat transfer goes down. So let's say this is staying constant. So before we go to how it affects it, so ambient temperature goes down. This remains the same. That means the refrigerant moving through the condenser is gaining heat, right? Because now the heat transfer is out of balance. It's not rejecting as much heat as it's bringing to the condenser, which means, of course, the temperature has to rise. So T5 starts going up, meaning that approach gets bigger, the pressure gets larger, and you reach a new equilibrium point. In this case, if everything else stays the same, if T infinity rises by, say, 10 degrees, then T5 will have to rise by 10 degrees as well, and that's associated with an increase in the condensing pressure. For any given set of circumstances, there's really only one equilibrium point, and that's what determines the condensing pressure in these systems. So I've really struggled with this, so bear with me. I think we can understand it. So here's a simple kind of cartoony sort of graph where you have the heat transfer on the vertical axis, condensing pressure on the horizontal axis, and the blue line represents the thermodynamics. That's the amount of heat that's being driven, brought to the condenser by the refrigeration system. I've showed us a modestly decreasing line. It could be flat. I think it's going to vary on a case-by-case basis. The condenser performance given by that heat transfer equation is a series of lines. Each given line is for a given U. So as the condenser pressure increases, the approach gets bigger and it moves up this line, right? But if you change the conditions of the condenser by increasing the airflow through it, you jump to a different line. So imagine, for example, you're sitting here at this equilibrium point where these two lines intersect, and the outside temperature goes up. Okay, so that means your approach goes down, and the condenser pressure has to increase until you get to an equilibrium point, and I'll say maybe it's this equilibrium point. So we're at a much higher condensing pressure, and a lower effective heat transfer coefficient because of the way the temperature affects the transfer coefficient. If we want to go back to that original condensing pressure under that higher outside condition, you have to jump up to you have to increase the U again by maybe running more air through it, turning the fans on higher, and that brings you back to a new equilibrium position. So there's a trade-off here going on between what the compressor is doing and what you have to do in the condenser to make it all work together. So condensers have control systems. They can be as simple as like a mercury switch, a little switch right on the coil that senses the temperature. If that temperature gets too high, it kicks on another fan, or maybe kicks in another condenser. Sometimes there's multiple condensers. They share the load between them. Multi-speed control. There could be fans that have multiple speeds, but the best approach is a variable frequency drive on the condenser fan. It really minimizes the work. If you run that fan at half speed, you're getting about half the condensing capacity, but it's only about 1/8 of the work because of what's called the affinity laws, right? Of how fan work goes with its speed. And so the most efficient system, we really haven't run across these very often, though the folks at Simplot were doing this. It's called a wet bulb approach. So you're constantly monitoring the wet bulb temperature outside. You add the approach, usually 20 to 30 degrees Fahrenheit, and say add that to the wet bulb temperature, and that's the condensing temperature, and hence the condensing pressure you want to operate at. So let's wrap that up. It's been a little over 20 minutes. We will go on to how to analyze this. How do you to figure out what the impact of all this varying weather conditions are on the energy consumption of the condenser. So thanks.